Hi everybody, this is Mrs. T for Mrs. T's Chem Talk. This is going to be a video on Regents Review, but it looks like that's not going to happen. So I think what I'm going to do is play the video during the live stream and take questions via Remind during the time that we said the live stream would be. Mrs. Tamanello, my chemistry teacher at Calhoun High School, and during this video I'll be going through some Regents Review topics. First topic will be physical behavior of matter, and the first thing that we're going to cover would be some heat formulas. These heat formulas would be found on table T and table B. So if you have a question asking you about a temperature change, how much heat, how much thermal energy is exchanged when this mass of water changes from one temperature to another, you're going to subtract the two temperatures to get the delta T, and you're going to use the formula Q equals mc delta T. The C value, which is the specific heat of water, is found on table B, and M stands for mass in grams. Your Q will come out in joules. If instead there is a phase change for melting or freezing, you're going to use the formula Q equals MHF. HF stands for the heat of fusion. Heat of fusion of water, again, is found on table B. And for boiling or condensing, you'd use the formula Q equals mHV. And the HV value is your heat of vaporization, and that's also found on table B. The next topic that was asked about would be the heating curves. So when we talked about heating curves, we said that if we have 1, 2, 3 slanted lines, that those 3 slanted lines would represent solid, liquid, and gas. We said that any flat lines or lines parallel to this x-axis here would be phase changes. Going from solid to liquid is called melting. Liquid to solid is called freezing. Liquid to gas is called vaporization. Gas to liquid is called condensation. The heating curve, because it goes uphill in terms of energy, is endothermic, which means that in the heating curve we are absorbing we are increasing the amount of energy that the sample has as it absorbs heat. When it is in a single phase, the temperature is changing, so the kinetic energy is changing. At a phase change on the heating curve, the potential energy is changing. And I should undo that and put that here. If we were talking about the cooling curve, the reverse direction, when we go downhill, that's exothermic. So if we're going downhill, temperature decreasing, kinetic energy is decreasing, phase change on the cooling curve, potential energy is decreasing. Distillation was another thing that people asked about, and we use distillation to separate mixtures of substances that have different boiling points. And we heat up a mixture. As we heat it up, the vapor goes into the condenser, and there is some water surrounding this that cools what's inside the condenser, so that then that liquid, so that that vapor can turn into liquid and be collected in the flask. Sorry, I just went completely backwards. We are going to heat the mixture in this flask so that it turns into a vapor and can be collected into this flask. I was looking at it backwards. The first piece of the mixture that gets collected here in the distillate would be the substance with the lowest boiling point. In the chapter for atomic structure, people asked about the bright line spectrum. Remember that when an atom absorbs energy, electrons move up to the excited state, This is a temporary state when the electrons are in a higher energy level, further away from the nucleus. Eventually, the electrons will move back down to the ground state. When the electrons move from excited state to ground state, energy is released in the form of light. We can separate this light into the line pattern of the bright line spectrum. Every element has its own unique bright line spectrum that can be used to identify substances or elements that are found in a mixture. When we talk about isotopes, remember that isotopes have the same number of protons, but they have different numbers of neutrons, and that would be evidenced by they have the same atomic number, but a different mass number. The mass number is protons plus neutrons minus the atomic number, which is protons only, gives us the number of neutrons. So this one here has 5 neutrons, 4 neutrons, and 3 neutrons. So same atomic number, same number of protons, different numbers of neutrons makes these isotopes of each other. When we have these isotopes, someone asked about atomic mass versus mass number. When we look at these isotopes have different atomic masses. Or isotope masses, and these different isotope masses also have different abundances. When we look, the mass number is simply protons plus neutrons, but the isotope mass is a number that goes out to decimal places. The atomic mass takes into account the percent abundance times the atomic mass. So you do percent abundance times the atomic mass of the isotopes. Percent abundance times the atomic mass or the isotope mass. And when we add those 3 results together, we get the atomic mass that's found on the periodic table. Remember that the atomic mass on the periodic table is an average that takes into account the percent abundances and the isotope mass of the naturally occurring isotopes. When we talk about electron configuration, the electron configuration is found on the bottom of every element on the periodic table. Each number represents the number of electrons in each successive shell. The maximum for the first shell is 2. Maximum for the second shell is 8. Maximum for the third shell is 18. Maximum for the fourth shell is 32. Some elements, if their atomic number is 72 or higher, skips the 2-8 in their electron configuration. So if you see an electron configuration that starts with 18, that means that the 2-8 has been omitted just because it wouldn't fit. The next topic would be nuclear chemistry, and certain nuclear equations will be demonstrated. So for example, if you see a really big really big mass number, neutrons before the arrow, 2 smaller pieces, and more neutrons after the arrow, that would be fission. If you see H plus H making He, that's fusion. 2 small isotopes combining for 1 slightly larger. That's fusion. If you just see 2 pieces before the arrow with all different element symbols, that's just artificial transmutation. And when you see 1 species before the arrow giving off alpha or beta or positron and then turning into something else, this is natural transmutation, and it also happens to be alpha decay. When we're talking about half-life, remember that half-life is the amount of time it takes for half of a radioactive sample to decay into more stable products. Every half-life period will see the amount remaining unchanged divide in half, so 10 to 5, 5 to 2.5, 2.5 to 1.25. And we can also take an amount and just say, okay, after one half-life it divides in half, another half-life it divides in half again. Each half-life period shows that the amount remaining as the original substance is dividing in half. In the periodic table chapter, when we talk about periodic trends, ionization energy increases across the table. So does electronegativity. And the reason why this happens across a period is because of increasing nuclear charge. We also have the atomic radius getting smaller as we go across because of this increasing nuclear charge. Atomic radius, however, when you go down a group, increases because of this increasing number of shells. We also have more shielding. These shells get in the way of the ability of the nucleus to hold on to those valence electrons. So that also makes the valence electrons easier to remove. So the electronegativity decreases, and so does the ionization energy as we go down, whereas electronegativity and ionization energy both increase as we go across because there's more positives in the nucleus to pull in those negative electrons. And just going back to periodic trends, just remember that all of that can be looked up on table S. Also remember that as we go across and up, over here we have fluorine, which is our most non-metally non-metal, and down here we have francium, which is our most metallic metal. So closer to francium is more metallic, closer to fluorine is more non-metallic. In the chapter of bonding, don't forget about your bond types. Covalent is sharing electrons. We make molecules. Those molecules are soft, poor conductors, and have a low melting point. I usually use the word splash for molecular substances, soft, poor conductors, low melting point. Ionic bonds include the transfer of electrons, making ions. Ionic compounds are hard with a high melting point, and they conduct in liquid and solution when their ions can move. Metallic bonds consist of single metals, so like just a sample of silver or just a sample of gold. Their positive ions immersed in a sea of mobile electrons. And these metals, remember, they're shiny, which means they have luster. They're malleable and ductile, which means moldable or you can hammer them into thin sheets. Ductile means that you can draw them into thin wires without them breaking. And they are good conductors in all phases because of their mobile electrons. Their mobile electrons allow them to conduct electricity. Covalent dot diagrams, remember that you can either use lines in between or each line represents two dots. Nitrogen, N2, remember, shares 3 pairs of electrons or 6 electrons between. Carbon dioxide has 2 double bonds and a linear shape. Water has a bent shape and remember has a slightly negative oxygen side and a slightly positive hydrogen side. Remember, for molecules, symmetrical is nonpolar, asymmetrical is polar. Water is asymmetrical polar, whereas the nitrogen and the carbon dioxide are symmetrical nonpolar. Remember also that like dissolves like, so water will dissolve other polar asymmetrical molecules, and symmetrical nonpolar molecules will dissolve in each other. So again, for molecules, symmetrical is nonpolar, asymmetrical is polar. Like dissolves like, which means that polar water will dissolve other polar molecules. Nonpolar substances like benzene will dissolve other nonpolar substances, and something like oil that is nonpolar will not dissolve in water, which is polar. When we talk about intermolecular forces of attraction, which is IMF, remember that dispersion forces are in all molecules and atoms and are the only type of intermolecular force when we have a nonpolar molecule. Dipole-dipole is when the positive side of one polar asymmetrical molecule attracts the negative side of another. And hydrogen bonding exists when, inside of a molecule, hydrogen is bonded to fluorine, oxygen, or nitrogen. This intermolecular force between molecules is stronger than expected and accounts for the higher than expected boiling point of water. When we talk about ionic dot diagrams, remember that we put the metal in brackets with no dots, positive charge from the table, non-metal in brackets with 8 dots, negative charge from the table. If the charges are equal and opposite, you need one of each. Again, equal and opposite, one of each. When they are not equal and opposite, you need to have the right ratio of negatives to positives so that they add up to 0. Who want a quick significant figure brush up? When we talked about counting significant figures, we said we would divide numbers or split them up into Pacific, which is decimal present, and Atlantic, which is decimal absent. When a measurement has a decimal point, it is the zeros prior to the first non-zero digit that are not significant figures here. There are no non-zero digits on the Pacific Ocean side here, right? Pacific, Atlantic. So this has 1, 2, 3, 4, 5, 6 on the Pacific side. So this has 3 significant figures. When you have a decimal absent, it is the Atlantic zeros that are, sorry, I did this backwards here, that are not significant figures. So here, these are your significant figures. This has 2 significant figures. This has 1 significant figure. And here, there are no zeros at all. So there are 4 significant figures. Remember, if you have to count significant figures, when there's a decimal absent, the zeros on the Atlantic side are not part of the measurement, are not significant figures. When you have a decimal present, the zeros on the Pacific side are not part of the measurement and are not significant figures. When you are finding crisscross formulas, remember that you look up the symbols, you look up the oxidation numbers, crisscross, drop the signs to get the formula. If you have an 8 or an 8, you're going to look on table E, calcium, periodic table with a +2 charge, nitrate on table E. I put the formula of the ion in parentheses with the charge on the outside, crisscross to the outside of the parentheses, drop the signs. If the number that's coming down is not a 1, we keep the parentheses and put the subscript outside the parentheses. When you have a number in parentheses, they are giving you the charge of the first element. So iron 2 means iron with a +2. Manganese 4 means manganese with a +4. Remember, if the two numbers can be reduced before we crisscross, we do that. So we'd get MnO2 there. Remember also, if at any point this is going too fast, you can pause, you can rewind, you can rewatch parts if it's going too fast for you. When you are finding the gram formula mass, remember that you are supposed to take the subscripts times the formula mass, or the atomic mass, I should say, on the periodic table. I usually round to the 10th before I multiply. Then you add those numbers up. That mass in grams is the mass of 1 mole of the substance. That mass in atomic mass units is the mass of 1 formula unit for ionics, or the average mass of 1 molecule for covalent substances. When we do percent composition by mass, remember that we find that gram formula mass and then we do mass of part over mass of whole times 100. Remember that this formula is on table T for you, so you don't have to memorize it. So the mass of carbon's part was 72. The mass of the whole was 180. 72 divided by 180 times 100 would be the percent composition by mass of carbon in glucose. When you're balancing equations, remember we're going to use coefficients, and in order to balance this arrow here should be like an equal sign. So we have 1C here and 1C there, 4 H's and 4 H's, but our O's are not equal. So we are going to put a coefficient in front of the oxygen so that we can balance out those molecules. We want the same number of atoms on each side in order to show balancing, and this will show that the law of conservation of matter has been abided by. The next chapter was solutions. And some people asked about molarity. When we were talking about molarity, we know that this formula is on table T. It is a formula for concentration. And if we have a question that says, what is the molarity of a solution containing 0.32 moles in 3.4 liters? Notice moles goes over liters. So we would do 0.32 divided by 3.4, and when we divide that out, our answer would be in big M, and it comes out to 0.094 molar, or 0.094 moles per liter. Oh, here we go. There is the work and the solution for that question. The other way that we can do concentration is in parts per million. And remember that parts per million is part over whole times 1 million. If we had 0.008 grams of silver chloride in 100 grams of water, that would mean that my total amount of solution is 100.008. We would put the part over the whole times 1 million. Now, because 100.008 and 100 are so close, we can just do it over 100, but the most important part is to remember that in parts per million, instead of multiplying by 100 like we do in percent, we multiply by 1 million so that these numbers are more usable. 80 parts per million is a lot easier to work with than the percent, which would have been lots of zeros in the front. It would have been a really small number. Electrolysis. when we're talking about, electrolytes, when we're talking about solutions that do, we're talking about just plain water. We did this experiment. Plain water will not conduct electricity. Sugar water will not conduct electricity, but salt water will, and salt water will conduct electricity because the salt dissolves and makes ions that can move. Those ions are able to carry the charge and conduct the electricity to light the light bulb. Anything that is soluble on table F will be able to do this. When we look at table F, remember that we are going to use table F to find out whether an ionic compound is soluble. Remember that group 1 ions, ammonium, nitrate, acetate, hydrogen carbonate, and chlorate, are all soluble with no exception. So if you see this at the beginning of a formula, or any group 1 ion at the beginning of the formula, or if a formula ends in NO3, ends in acetate, ends in hydrogen carbonate, or ends in chlorate, those compounds will be soluble no matter what. If something has chloride and silver, it's insoluble. Chloride without one of these, it is soluble. If something has one of these parts, just one of these without an exception, it's insoluble. If it has one of these with its exception, it is soluble. Remember that table G shows us solubility curves, and when we're talking about solubility curves, remember that this is the plot of a saturated solution for potassium iodide. This is the number of grams that you can put into 100 grams of water at these temperatures and get all of it to dissolve, as well as have it dissolve in an equilibrium. If we want to talk about a different substance, each substance has its own plot of a saturated solution. If we put in less than the saturated solution, this would be called an unsaturated solution. If we make a saturated solution and then cool it so that that amount is still dissolved and it stays dissolved, that would be a supersaturated solution, which would be a temporary condition. When we're talking about acids and bases, remember that table K has common acids, table L has common bases. You should know that acids tend to taste sour. They have a pH of less than 7. They put H+ ions in aqueous solution. They corrode all metals that are more active than hydrogen on table J. They react with metals to produce a compound and hydrogen gas. Again, the metals that are more active than hydrogen on table J will do this. And they turn litmus red. Bases tend to taste bitter. They tend to feel slippery. They have a pH greater than 7. They put hydroxide into solution. They don't corrode or react with metals, and they turn litmus blue. Acids tend to have H's in the front or COOH at the end, and bases tend to be a metal in front of OH. When we're talking about the pH scale goes from, generally speaking, 0 to 14, and the pH scale is the negative log of the hydrogen ion concentration. Because every place on the pH scale is a factor of 10, increasing the pH by 1 makes it 10 times more basic. Decreasing the pH by 1 makes the solution 10 times more acidic. Neutralization is always acid and base, making salt and water, and we use the formula MAVA equals MBVB in order to do calculations for a titration, which involves neutralization. When we're talking about kinetics and equilibrium, remember that an endothermic reaction goes uphill, an exothermic reaction goes downhill. Remember that when we're talking about these potential energy diagrams, if we're talking about anything that hits the x-axis, we're talking about the potential energy of that particular position. Above the reactants to the top is forward activation energy. Above the products to the top is reverse activation energy. And if we take our potential energy diagram and separate it into 3 sections where it's top to the products to the reactants and then the bottom, the top bun, we have the bottom bun, and then we have our middle part here, which is our delta hamburger. So bun, bun, hamburger. The delta hamburger is the delta H value, which is also known as the heat of reaction. For an endothermic reaction, that heat is taken in on the reactant side. For an exothermic reaction, that heat is given off on the product side. Remember that we have 5 factors that can affect the rate of a chemical reaction: temperature, concentration, surface area, catalyst, and nature. And remember that a catalyst, although it does speed up a reaction, a catalyst gives us an alternate reaction pathway, lowering the activation energy. However, a catalyst does not affect equilibrium. Adding a catalyst at equilibrium will speed up both the forward and reverse reactions equally, therefore keeping us at equilibrium. Remember, this could be for a physical change or a chemical change. We will have equal rates and constant concentrations, so the rate of the forward reaction will equal the rate of the reverse reaction. Away from something added, shift towards something removed, and if we increase pressure, we'll shift to the right. Adding a nitrogen, we'll shift away from the nitrogen. If I remove hydrogen, we will shift towards the hydrogen, which would be left. And if I increase pressure, on this side I have 1 gas plus 3 gas. I have 4 gas. On this side, I have 2 gas. Increasing pressure will shift to the side with less gas, which means it will shift to the right. In the chapter of redox, when we're doing half reactions and balancing half reactions, the first thing we need to do is put in oxidation numbers. Remember that when something is by itself with no charge written, its oxidation number is 0. Nonmetals get a negative charge, and chlorine's negative choice is -1. That makes the copper here a +2. That makes the zinc here a +2. +2 minus 2 has to add up to 0. My chlorines are spectators because their charges don't change. Therefore, I will not write those in my half reactions. Remember that Gur is said by Leo. Gaining electrons is reduction and the charge goes down. Electrons before the arrow. Losing electrons is oxidation and the charge goes up. And electrons go on the right side of the arrow. So if zinc 0 turns into zinc +2, this is going to be an oxidation because the charge is going up, and it's a loss of 2 moles of electrons. If Cu +2 is turning into Cu0, this is a reduction, and it must be a gain of 2 moles of electrons. So these have the same numbers of electrons in each, therefore their half reactions are already balanced. When we talk about voltaic versus electrolytic cells, remember that voltaic cells, which are also called galvanic cells, are spontaneous. redox reactions, where a redox reaction, which is a chemical reaction, produces electricity, whereas in an electrolytic cell, we require a power source because it is a non-spontaneous reaction, and we are going to take that electrical energy and convert it into chemical energy. We always have electrons flowing through a wire from anode to cathode. So if the electrons are flowing towards the spoon, that makes the spoon the cathode. We always have one side of oxidation and one side of reduction, but in the Voltaic cell, those reactions happen spontaneously. In an electrolytic cell, those reactions are caused by an outside power source. For the chapter of organic chemistry, when we talk about molecular versus empirical formula, the molecular formula, you're just going to count up 2 C's, C2. 1, 2, 3, 4, H4. Oops. 1, 2, O, O2. So this would be my molecular formula, whereas my empirical formula, I'm going to take those same symbols, but I'm going to reduce the subscripts like I would reduce a fraction. I'm going to put them in lowest form, so that means I can divide them all by 2. So it would just be C, H2O would be the empirical formula. Tables P and Q have our prefixes. These prefixes are always for the numbers of carbons, and alkanes, remember, have all single bonds and are saturated. Alkenes and alkynes, oops, I'm coming off the screen here, but are unsaturated because of the presence of a double or a triple bond. You need all single bonds to be saturated. Remember that for saturated, that has all single bonds, undergoes substitution. Substitution has 2 products. So here we go. 1 chlorine changes places with 1 H. The H comes out and the chlorine goes in. 2 different products, starting with single bonds. This is a substitution. For addition, you start with a double or a triple bond, and you will only make a product. Both of them go in, because when this double bond turns into single, both chlorines have room to come in. So this over here is addition. When you're talking about fermentation, you're always going to have sugar making ethanol and carbon dioxide. Remember, alcohol and bubbles are what's in beer. Yeast, the enzymes in yeast, is what catalyzes that reaction. Saponification is always fat and base, and makes soap. Remember, SAPO can be rearranged into soap. Combustion, remember, is always combining with oxygen, making carbon dioxide and water. And esterification is always acid plus alcohol, making ester. Polymerization, remember, is the one with the N's, okay? We're taking lots of these and combining them into lots of these. I usually actually see it like this, where the N is in the front in the reactants and the N is at the end for the products, to show these are separate, these are connected. That is the end of what was meant to be this year's live stream. That's the review of all of the topics that you submitted to me and asked me to go over with you at this last moment here, very close to the Regents exam. If you have any other questions, feel free to contact me on Remind or over school email. And hopefully you are doing a lot of studying. Watch this video as well as the other ones in the playlist to help you to prepare for the Regents exam next week. And happy studying!